There is a simple belief most of us carry without noticing it. A red apple is red because redness belongs to it. A blue sky is blue because blueness fills it. A green leaf carries green the way it carries mass or shape. Color seems attached to objects. It feels stable. If you leave the room and return, the apple is still red. If someone else looks at it, they also call it red. The color appears to reside in the surface itself. This belief is quiet and persistent. It rarely invites examination. And yet, it is the starting point we must test. Physics does not begin by discarding intuition. It begins by holding it carefully and asking whether it survives constraint. So we pause with the claim, color is a property of objects. It feels obvious. It feels complete. But in science, obvious is not the same as correct. Before we move further, it is worth noticing how rarely we stop to question assumptions like this at all. Much of what feels most stable in our experience passes without examination, simply because it has never demanded our attention. If you find value in slowing down with questions that usually remain invisible, you can support this kind of careful exploration by liking the video. And if you would like to continue following these quiet investigations into the structure of physical reality, you may choose to subscribe. You are also welcome to share in the comments section where you are listening from tonight. It is always grounding to see how widely this curiosity is shared. Now we return to the apple. When you say it is red, what do you actually mean? Do you mean that redness is stored in its skin the way water is stored in a sponge? Do you mean that if the apple existed alone in darkness, it would still possess red within it? Or do you mean something else? Something less examined? At first, it feels unnecessary to press this question. The apple does not change color while you look at it. Its surface appears steady. Its redness seems independent of your attention, so the intuitive model remains intact. We treat the object as primary, and color as something it carries as naturally as texture. But this is only a claim. The idea has not been placed under pressure. No conditions have been withdrawn, no variables disturbed. It has been allowed to stand without resistance, and until a belief survives constraint, it is only comfort. So we hold the idea gently. Color belongs to objects. That claim rests on a condition so constant it rarely feels like a condition at all. Remove it, and the apple remains on the table, but something else does not. So we do the simplest thing possible. We turn off the light. The apple remains on the table. Its shape has not changed. Its mass is the same. Its surface chemistry is undisturbed. Every atom within it remains arranged exactly as before. The red does not linger. It disappears completely. In complete darkness, the apple is not red. It is not any color at all. It does not glow faintly with stored pigment. It does not preserve a hidden redness waiting to be revealed. The experience of red disappears entirely. If color truly belonged to the object in the way weight or texture does, darkness should not erase it. The apple would remain red whether or not anyone could see it. Yet without light, color has no presence in experience and no detectable physical expression. We might attempt to defend the intuition. Perhaps the red is still there, simply unseen. Perhaps light is only required to reveal it. This seems reasonable at first. After all, we cannot see shape without light either, yet we do not conclude that shape ceases to exist. So maybe color behaves the same way. But notice the difference carefully. Shape persists as a structural arrangement of matter. It can be measured in darkness by touch or by instruments that do not depend on visible light. The geometry remains physically defined. Redness does not persist in that way. There is no instrument that detects intrinsic redness in total darkness without introducing light. The moment you measure color, you must supply illumination. Without that interaction, There is nothing to measure. Already the original claim begins to weaken. If color were an intrinsic property, it would not require an external condition to manifest. Mass does not require illumination. Charge does not require visibility. Atomic composition does not depend on brightness. Yet color vanishes the moment light is removed. This is the first fracture in the intuitive model. The apple is still exactly where it was. The color is not. Only the conditions around it have shifted. We do not yet know what color is made of, but we now know something precise about what it is not. It is not independent of light. The belief that color simply resides inside objects has failed its first constraint. Bringing the light back does not restore certainty. The kind of light matters, and the apple responds to that difference. Now we restore the light, but not completely. Instead of bright midday illumination, imagine the apple under a dim lamp. Its surface is still visible. Its outline is intact. Yet the red is no longer vivid. It appears muted, darker, less saturated. Nothing in the apple has changed. The molecules in its skin remain arranged as before. The pigments embedded in its surface are still present, and yet the experience of red has shifted. If color belonged entirely to the object, it should not fluctuate with brightness. The apple would carry the same redness regardless of intensity, but it does not. Now change the light again. Replace the neutral lamp with a warm, yellowish bulb. The apple now appears deeper, almost orange in tone. Under a cooler bluish light, the red sharpens and shifts again. In sunset light, it glows richly. Under fluorescent light, it can look dull or uneven. The object remains structurally constant. The perceived color does not. At this point, the intuitive claim strains further. If redness were stored in the apple the way sugar is stored in its flesh, illumination would merely reveal it. It would not reshape it. Yet the color seems sensitive to the character of the light itself. A different possibility begins to take shape. Perhaps color is not solely in the object. Perhaps it is partly in the light. But even that idea must be tested carefully. If the apple's color depends on illumination, then color cannot be fully intrinsic. It requires interaction. It depends on conditions. It responds to variation. And we are only adjusting brightness and tone so far. We have not yet altered the structure of the light in a fundamental way. Still, something important has already occurred. The belief that objects carry stable color independent of environment has failed twice. First in darkness, where color vanished completely. Then under changing illumination, where color shifted without any alteration in the object itself. The pattern is emerging quietly. Color does not behave like a stored property. It behaves like a response. But a response to what exactly? We have removed one condition and altered another. The shift points toward the illumination itself, not its brightness or warmth, but what it contains. If color shifts with light, we must understand what light is made of before we can go further. If color vanishes without light and shifts when light changes, it is natural to move the intuition one step over. Perhaps color does not belong to the object. Perhaps it belongs to the light. When sunlight enters a room, the world appears richly colored. When only a red spotlight shines, everything within it looks red. Under deep blue illumination, surfaces take on blue tones. This makes it tempting to conclude that color travels inside the light itself, carried from source to surface. The idea feels stronger than the original claim. Light arrives from somewhere, it reaches the apple becomes visible, the red appears. So maybe redness is delivered by the light and simply reflected back to us. But we must examine this carefully. Consider a beam of white sunlight falling on a white wall. The wall appears white. Now place a red apple in that same beam. The apple appears red while the wall remains white. If the light itself were red, the wall would appear red as well. But it does not. This suggests that white light cannot be a single uniform color. It must contain something more complex. Now imagine passing that same sunlight through a glass prism. The single beam spreads out into a band of distinct colors: red, orange, yellow, green, blue, violet. The light was never purely colorless. It contained a range of components that were not visible until separated. This is the next fracture. If white light already contains many colors within it, then color cannot be created solely by the object. The object must be interacting selectively with something already present in the light. But this creates tension. If sunlight contains all visible colors mixed together, then why does the apple not appear white? Why does it not reflect all of them equally? The light arriving at the apple is broad and varied, yet the apple returns only a narrow range to our eyes. So color cannot belong solely to the object. Light alone is not enough to account for what we see. The color takes shape only when illumination and material structure meet. And to understand that interaction, we must look deeper than brightness or visible hue. We must examine what white light is actually made of at a physical level. Because if color depends on what light carries, then we must identify its internal structure. Only then can we see why certain parts survive the interaction with matter while others disappear. When white light passes through a prism and spreads into a spectrum, something important is revealed. The separation is not arbitrary. The colors appear in a continuous order, red at one end, violet at the other. Between them, a smooth progression. This tells us that white light is not empty brightness. It is a mixture. But a mixture of what? Physics describes light as electromagnetic radiation. That phrase can feel distant, so we move more carefully. Light carries energy. That energy is not uniform across all light. It varies. Each portion of the visible spectrum corresponds to a different amount of energy carried by the light itself. Red light carries less energy per unit than blue or violet light. The difference is not symbolic. It is measurable and precise. The spectrum revealed by the prism is not simply a painting of colors. It is a map of energy variation. White light, then, is a blend of many energy components traveling together. Now we return to the apple under sunlight. The light reaching it contains this entire range of energies: low energy components, higher energy components, everything in between. If the apple were indifferent to these differences, it would reflect them all equally, and the result would appear white as the wall does. But it does not. Instead, most of the incoming energies do not return to your eye. Only a narrow portion does. So the question sharpens. What determines which parts of the incoming light survive the interaction? Why does the apple send back mostly the lower energy red portion, while the higher energy components do not reappear? At this point, the intuition that color resides in light alone also fails. White light contains all visible energies, yet different objects under the same light return different colors. The light is constant, the objects vary, and so the governing mechanism must lie in the interaction between the internal structure of matter and the energy carried by the light. To understand that interaction, we have to go beneath chemistry, down to atomic structure, because the selectivity we observe suggests constraint, and constraint in physics usually begins at the smallest scales. We now hold two facts together. White light carries a continuous range of energies across the visible spectrum. The apple, under that same white light, returns only a narrow band to your eye. This selectivity demands explanation. If matter responded smoothly to incoming light, we would expect gradual absorption across the spectrum, perhaps some slight variation, but nothing sharply defined. Yet what we observe in the world is specificity. Copper appears metallic and reddish. Leaves appear green. A blueberry appears deep blue. Each object behaves as though it is filtering light according to an internal rule. This suggests that matter is not passive in the presence of light. It is constrained. To understand the nature of that constraint, we must let go of the idea that matter is continuous and uniform. At everyday scales, surfaces seem smooth, solids seem solid, but at the atomic level, matter is structured from discrete units, atoms, and within atoms, smaller structures still. An atom consists of a central nucleus surrounded by electrons. These electrons are not scattered randomly. They occupy specific allowed configurations. This is where the governing constraint begins to take form. Electrons inside atoms cannot possess arbitrary amounts of energy. They are restricted to discrete energy levels. They may occupy one level or another, but not the values in between. This restriction is not imposed externally. It arises from the quantum structure of matter itself. Now consider what happens when light reaches such a system. Light carries energy. Each component of the spectrum corresponds to a particular amount of energy. If an incoming portion of light matches exactly the energy difference between two allowed electron levels, the electron can absorb it. If it does not match, the light passes by without being absorbed in that way. This creates selectivity. Matter does not absorb light smoothly across all energies. It absorbs only those energies that correspond precisely to its internal quantum structure. All other incoming energies are left unabsorbed, and what is not absorbed remains available to be reflected or scattered. We are approaching the mechanism. The apple does not store redness as a substance. Its atoms impose restrictions. Only certain incoming energies are absorbed by electronic transitions within its molecules. The rest survive the interaction. The color you see is not what the apple produces. It is what the apple fails to absorb. This inversion marks a significant shift. Color may not be a positive property. It may be the residual outcome of constraint. Those energy levels are not flexible. Their quantized structure determines exactly which photon energies can be absorbed and which pass through untouched. To understand why absorption is selective, we must slow down and look inward. An atom is not a tiny solid sphere. It is mostly space. At its center sits a dense nucleus. Surrounding it is a structured region occupied by electrons. These electrons are not orbiting like planets. They exist in allowed states defined by quantum rules. Each state corresponds to a specific amount of energy. The crucial point is this: electrons cannot take on just any energy value. They are restricted to discrete levels. Between those levels, no stable state exists. This discreteness is not optional. It is a governing feature of quantum mechanics. Now imagine an electron resting in a lower energy level within an atom in the apple's skin. It remains there stably unless something provides it with exactly the right amount of energy to move to a higher level. Light carries energy in packets. Each packet corresponds to a specific frequency and therefore a specific energy. If the energy carried by a portion of incoming light exactly matches the gap between two allowed electron levels, the electron can absorb that energy and transition upward. If the energy does not match, the transition cannot occur. There is no partial acceptance, no gradual adjustment. Either the match exists or it does not. This is the source of selectivity. The atomic structure of a material defines a set of allowed energy gaps. Those gaps determine which portions of incoming light can be absorbed. All other portions remain unabsorbed. When white sunlight strikes the apple, its molecules present a specific pattern of allowed energy differences. Many incoming energies match those differences and are absorbed. Others do not. The absorbed portions do not return to your eye. The unabsorbed portions remain available to scatter outward. At this scale, color begins to look less like a surface property and more like a consequence of internal constraint. The apple's redness is not painted onto its skin. It is governed by the quantum architecture of the atoms and molecules composing it. The failure of our original intuition deepens. Color is not stored, it is selected. That selection is not vague or approximate. It depends on the exact size of the energy gaps available inside those electrons. Only light carrying precisely the right amount of energy can participate in a transition. All other incoming light encounters a boundary it cannot cross. The interaction is exact, and from that exactness, the visible world begins to take shape. Inside each atom, electrons occupy states that are sharply defined. These states are not positions in the ordinary sense. They are stable energy configurations permitted by quantum law. An electron in one of these configurations cannot drift slightly upward or downward in energy. It cannot hover between levels. It remains fixed until a precise interaction occurs. The gaps between these allowed levels are equally precise. Each gap represents a specific difference in energy, not a range, not an estimate, a fixed separation. When light encounters matter, it brings energy with it. But that energy also comes in discrete packets. Each photon carries a specific quantity determined by its frequency. Now, the constraint becomes clear. For an electron to move from one level to another, the energy delivered must match the gap exactly. If the photon carries too little energy, the electron cannot rise. If it carries too much, the excess cannot be stored. The transition fails. There is no negotiation between light and matter, only compatibility. This compatibility requirement creates a filter at the atomic scale. Out of the continuous spread of energies present in white light, only certain values are permitted to trigger electronic transitions. Everything else remains unaffected by that particular atom. When many atoms bind together into molecules, the situation becomes more complex but follows the same rule. Molecules also possess discrete energy structures. Their allowed transitions may differ from those of isolated atoms, but the governing principle remains unchanged. Energy levels are quantized. Transitions require exact matches. The apple's surface is composed of countless molecules arranged in structured patterns. Each molecular system presents its own set of allowable transitions. Together, they define which portions of incoming light can be absorbed. Absorption is not a general dimming. It is a selective removal, governed by internal structure. This means that color is already being shaped before any light leaves the object. Certain photon energies are removed from the reflected mixture because they satisfied the quantum conditions for absorption. What remains is not random. It is the remainder after constraint, and that remainder, as it travels outward, carries the signature of the atomic architecture it encountered. When a photon with the correct energy encounters a molecule in the apple's skin, it does not simply bounce away. Its energy is taken up by an electron and used to shift that electron into a higher allowed state. This is absorption. The photon, as a distinct packet of light, ceases to exist in its original form. Its energy has been transferred into the internal structure of the molecule. But this excited state is not permanent. Electrons prefer lower energy configurations. After a brief interval, the electron returns to a lower level. The stored energy must then be released or redistributed. Sometimes that energy is emitted again as light, but not necessarily in the same direction, or with the same energy. Often it is dispersed into vibrational motion within the material. The absorbed energy becomes part of the microscopic agitation of atoms. The important point is this: the absorbed photon does not reappear as part of the reflected beam that reaches your eye. From the broad spectrum of incoming sunlight, specific energies are removed because they match the internal gaps available in the molecules. Those energies are converted into other forms within the material. What remains after this selective removal is a modified distribution of photon energies. If the molecules in the apple absorb strongly in the blue and green portions of the spectrum, those components are largely eliminated from the reflected light. The lower energy red portion is left comparatively intact. That surviving portion travels outward. When it reaches your eye, it is interpreted as red. The color you see is therefore not something added to the light. It is what remains after subtraction. Absorption defines absence, and absence shapes perception. At this stage, the governing law is becoming clearer. The quantum structure of matter does not create color by generating new hues. It filters incoming energy according to precise internal constraints. What is allowed to remain becomes visible. What is absorbed disappears into microscopic transitions. Color begins to look less like a property and more like a pattern left behind after interaction. And that pattern is determined by the quantized energy architecture of matter itself. After selective absorption has removed certain photon energies, the remaining light does not simply vanish. It continues interacting with the surface of the material. Some of it changes direction at the boundary between air and the apple's skin. Some of it penetrates slightly, encountering additional molecules before emerging again. Some of it scatters in multiple directions due to microscopic irregularities in structure. What matters is not the precise path of each photon, but the composition of the light that ultimately leaves the surface. Because specific energies were absorbed, the departing light is no longer a full spectrum. It is a filtered spectrum. The distribution of photon energies has been reshaped. If blue and green components were preferentially absorbed, the light leaving the apple contains proportionally more red wavelengths. That imbalance is what travels outward into the surrounding space. This outward light is not carrying a label that says red. It is carrying a particular distribution of energies. When that distribution enters your eye, it stimulates your visual system in a pattern corresponding to what you call red. From the perspective of the apple, nothing red was produced. The apple imposed constraints. It absorbed what matched its internal energy gaps. The rest remained free to scatter. Color, at this stage, is clearly not an intrinsic pigment floating on the surface. It is the residual signature of selective interaction, and this residual signature depends not only on the internal energy structure of molecules, but also on how light interacts with the physical arrangement of the surface itself. A smooth, polished material reflects differently than a rough one. A translucent layer modifies the path of light differently than an opaque layer. Microscopic structures influence how deeply light penetrates before emerging. All of these factors shape the final mixture of photon energies that leave the object. But beneath these variations, the governing constraint remains unchanged. Absorption is quantized. Selection is precise. The reflected light is a remainder defined by what the material could not accept, and that remainder is what moves outward to meet the next system in this chain of emergence. So far, we have focused on absorption at the level of molecular energy gaps, but the story does not end at internal transitions. The physical structure of a surface also shapes the light that leaves it. If a surface is smooth at microscopic scales, incoming light tends to reflect in organized directions. If it is rough, light scatters more diffusely. The difference does not usually change which photon energies survive absorption, but it changes how they are distributed in space. This affects brightness and sheen. A polished red apple appears glossy because reflected light maintains some directional coherence. A matte red surface appears softer because scattering spreads the remaining red light more evenly. Beyond texture, deeper structural effects can alter color itself. In some materials, layers or microscopic patterns cause certain wavelengths to interfere constructively or destructively. This is not absorption through electron transitions alone, but structural filtering through geometry. Thin films, microscopic ridges, and repeating patterns can enhance specific wavelength ranges while diminishing others. The internal quantum constraints still determine what can be absorbed, but structural arrangement determines how the surviving light recombines and exits. This reveals another refinement. Color is not governed by a single mechanism. It emerges from layered constraints. First, quantum energy levels determine which photon energies are removed through absorption. Then, physical structure shapes how the remaining energies are reflected or scattered. The visible outcome depends on both. The apple's red is therefore not a simple molecular fact. It is the combined result of molecular energy gaps and the physical arrangement of its surface tissues. The failure of our initial intuition continues to deepen. There is no isolated reservoir of redness inside the object. There is a structured system interacting with structured light, and the color that appears is the outcome of that interaction unfolding across multiple scales. Yet even this is not the final stage, because light leaving the apple has not yet become color in experience. It must still encounter another structured system, and that system will impose its own constraints. Not all color arises in exactly the same way. Many objects, like the apple, owe their appearance primarily to pigments. Pigments are molecules whose electron energy structures absorb specific portions of incoming light. Their color emerges from selective absorption governed by quantized transitions. But there is another category of color that does not depend mainly on pigment at all. Consider the shimmering blue of certain butterfly wings, or the shifting colors seen on a soap bubble. In these cases, the material itself may be nearly transparent. The color arises from microscopic physical structures that manipulate light through interference. When light encounters layered structures spaced at scales comparable to its wavelength, portions of it reflect from different depths and recombine. Some wavelengths reinforce one another, others cancel. The result is selective enhancement without relying primarily on electronic absorption. Yet even here, the process remains constrained by the same underlying physics. Light consists of discrete photon energies tied to wavelength. Matter possesses structured geometry at microscopic scales. The interaction between these two determines which wavelengths are amplified or diminished. In pigment-based color, selection occurs mainly through quantum energy gaps inside molecules. In structural color, selection occurs through spatial arrangement and wave interference. The mechanisms differ, but both rely on constraint. Both depend on the structured interaction between light and matter. Neither involves a stored substance called color. This comparison strengthens the failure of the original intuition. If color were simply a property contained in objects, it would not arise from two fundamentally different mechanisms governed by distinct constraints. Instead, color appears whenever light encounters structure capable of selective interaction. Whether through absorption or interference, the outcome is a modified distribution of photon energies. That modified distribution is what continues outward, and it still has one more boundary to cross before it becomes the color you experience. The light that leaves the apple carries a particular distribution of energies. That light travels outward in all directions. Most of it disperses into space. A small portion enters your eye. At the front of the eye, the cornea bends the incoming light. The lens refines its focus. The light converges onto the retina, a thin layer of neural tissue lining the back interior surface. The retina is not passive. Embedded within it are photoreceptor cells. These cells contain specialized molecules that respond to incoming photons. The response is not symbolic, it is physical. When a photon reaches one of these molecules, it may be absorbed if its energy matches a permissible molecular transition. The same principle we saw in the apple's molecules now operates again inside your eye. The photoreceptor contains a light-sensitive molecule whose electrons occupy allowed energy states. If the photon's energy aligns with the required difference between those states, absorption occurs. A molecular rearrangement follows. That rearrangement triggers a cascade of biochemical events. Ion channels shift. Electrical signals form. The signal travels along neural pathways deeper into the brain. The important point here is restraint. Your visual system does not measure the full continuous spectrum of incoming light with infinite resolution. It samples. There are 3 primary classes of cone photoreceptors in the human retina. Each class is most responsive to a different range of photon energies. One responds more strongly to longer wavelengths, one to intermediate, one to shorter. Each type still obeys quantum constraints. It cannot absorb arbitrary energies. It has a response curve shaped by its molecular structure. So when the filtered light from the apple enters your eye, it does not generate a label. It produces a pattern of activation across these 3 receptor classes. That pattern becomes the basis for color experience. Notice how the chain now extends across systems. Light, structured by energy distribution. Matter, structured by quantum energy levels. Biology, structured by molecular sensitivity ranges. At each stage, constraint governs interaction. Color has not yet appeared as a substance anywhere along this chain. It is emerging as a relational outcome distributed across multiple physical systems. The 3 classes of cone photoreceptors do not divide the spectrum into neat thirds. Each has a broad sensitivity curve. The one most responsive to longer wavelengths still responds weakly to some intermediate wavelengths. The middle range cones overlap significantly with both neighbors. The short wavelength cones taper off gradually rather than ending sharply. This overlap is essential. When light from the apple enters your eye, it does not activate only one receptor class. It produces a ratio of activation across all 3. If the reflected light contains a high proportion of longer wavelengths and relatively fewer shorter ones, the long wavelength cones respond more strongly. The middle range cones respond moderately. The short wavelength cones respond minimally. The brain does not measure absolute energy. It compares relative activity. Color perception is therefore constructed from proportional differences in neural response. This introduces another constraint. Human color vision is 3-dimensional in its sampling capacity. No matter how complex the incoming spectrum may be, it is reduced to 3 channels of information. That reduction means different spectral distributions can produce identical receptor ratios. 2 physically distinct mixtures of light can generate the same pattern of activation in the cones. When that happens, the perceived color is the same. The visual system cannot distinguish between them because it does not measure the full spectrum directly. It measures 3 overlapping response curves. The richness of visible color arises within this limitation. We do not perceive electromagnetic energy directly. We perceive the comparative response of 3 quantum-sensitive molecular systems embedded in neural tissue. The experience of red is not stored in the apple. It is not traveling intact through space. It is constructed from a ratio of activations inside your retina. The chain of interaction now includes light, matter, and biological sampling. Each stage imposes structure. Each stage filters possibility. Color continues to take shape, not as an object, but as a constrained relational event distributed across systems. Because your visual system reduces the incoming spectrum to 3 overlapping response channels, something subtle becomes possible. 2 beams of light can be physically different in their detailed energy composition and still produce the same pattern of cone activation. Imagine one light source that contains a smooth, continuous spread of wavelengths weighted toward the red end of the spectrum. Now imagine a second light source made from a narrow mixture of just 2 wavelengths, carefully chosen so that their combined effect stimulates the 3 cone types in the same proportions as the first source. Physically, these 2 lights are not the same. Their spectral structures differ. If measured with a spectrometer, the difference would be clear. Yet to your visual system, they are indistinguishable. They appear as the same red. These pairs are called metamers. They reveal something important. Color perception is not a direct reading of the external spectrum. It is an internal equivalence class defined by receptor-response ratios. Different physical causes can converge to the same perceptual outcome. This convergence further weakens the idea that color is a fixed attribute residing in the world independent of observers. If 2 distinct spectral realities produce identical experiences, then the experience cannot uniquely specify the external energy distribution. The visual system does not reconstruct the spectrum in full detail. It compresses it. Within that compression, distinctions that exist physically may disappear perceptually. The apple under sunlight and the apple under certain artificial lights may stimulate your cones in nearly identical ratios, even if the underlying light sources differ significantly in structure. The stability of perceived color is therefore not a simple reflection of external uniformity. It is a product of biological constraint interacting with physical constraint. The world presents structured light. Your retina samples it in 3 broad channels. From that sampling, a consistent experience arises. But that consistency does not guarantee uniqueness. Color, as experienced, tolerates multiple physical realizations beneath it. There is another layer to this construction that is easy to overlook. If color depended only on the raw ratios reaching your cones, then every shift in illumination would dramatically alter the appearance of objects. Under the golden light of late afternoon, everything would seem permanently tinted. Under the cool cast of overcast daylight, the world would shift again. And yet, most of the time, a red apple still appears red, whether you see it at noon, at sunset, or under indoor lighting. This stability is not coming from the apple alone. It is not coming from the light alone. It arises from additional processing within the visual system. Your brain does not interpret cone activation in isolation. It compares regions of a scene to one another. It evaluates contrast between surfaces. It infers the likely characteristics of the illumination and adjusts its interpretation accordingly. If the entire environment shifts toward longer wavelengths because of sunset light, the brain detects that this shift is global. It compensates. The relative differences between objects are preserved, and perceived colors remain comparatively stable. This process is known as color constancy. It is not perfect. Under extreme lighting conditions, color perception can shift noticeably. But within ordinary ranges, the visual system actively stabilizes the world. This means that the color you experience is not a simple output of photoreceptor chemistry. It is the result of layered interpretation applied to those initial signals. Quantum energy transitions in the apple filter the light. Quantum-sensitive molecules in your retina convert that filtered light into neural activity. Neural networks then adjust those signals in context. By the time you say the apple is red, multiple systems have contributed. The physical spectrum has been modified. The biological sampling has compressed it. The brain has interpreted and stabilized it. The color that seems immediate and intrinsic is in fact the outcome of distributed processes spanning external physics and internal computation. The original belief that color resides in objects now appears increasingly insufficient. What seemed simple has unfolded into interaction across scales. If we pause here and ask again whether red of the apple exists, the answer is no longer simple. It is not fully in the apple. The apple contains molecules with specific quantum energy gaps. Those gaps determine which photon energies are absorbed. But the apple does not generate redness on its own in darkness. It is not fully in the light. Sunlight contains a wide distribution of photon energies. Those energies exist whether or not they strike the apple. Yet without selective absorption, white light remains white. It is not fully in the eye. The retina contains 3 classes of cone receptors with overlapping sensitivity curves. They translate incoming photon energies into neural signals. But without structured light entering the eye, there is no color experience, and it is not solely in the brain. Neural circuits stabilize and interpret signals, but they cannot construct red from nothing. They require patterned input shaped by physical interaction. Color does not sit at a single location in the chain. It appears only when every layer is active. Light must carry a range of quantized energies. Matter must selectively absorb according to its internal quantum structure. The remaining energies must reach a visual system equipped with constrained sampling mechanisms. Neural processes must interpret relative activation patterns within environmental context. Remove any one of these layers and the experience dissolves. The redness of the apple is therefore not a property stored in its skin, nor a simple feature of the photons traveling through space. It is an event that occurs when structured energy meets structured matter and is then translated by structured biology. What feels like a static quality is actually a dynamic alignment across systems. The original intuition has not just weakened, it has been replaced by a more intricate picture in which color has no single address. It exists only in relation. When we place all the layers side by side, a pattern becomes visible. At the level of light, energy is distributed across a spectrum. That distribution is quantized at the level of individual photons, each carrying a specific amount of energy tied to its frequency. At the level of matter, electrons are restricted to discrete energy states. Only certain photon energies can be absorbed, because only certain transitions are allowed. This creates selective removal within the incoming spectrum. At the level of surface structure, geometry influences how the remaining light is redirected. Reflection, scattering, and interference reshape the outgoing distribution further. At the level of biology, 3 overlapping receptor classes sample that outgoing distribution. Their quantum-sensitive molecules respond according to their own constrained energy tolerances. At the level of neural processing, comparative evaluation and contextual adjustment stabilize perception under changing illumination. None of these layers independently contains color. Each layer modifies energy flow according to its own structural rules. Color appears only when the entire sequence operates together. This is emergence. Not emergence as mystery, but as structured dependency. A property that cannot be reduced to a single component because it arises from the interaction of multiple constrained systems. The apple's red is the visible expression of quantized energy interacting with quantized matter, filtered by geometry, translated by molecular receptors, and stabilized by neural comparison. If we isolate any one layer, color disappears. Light without matter is invisible brightness. Matter without light is dark structure. Receptors without incoming photons are silent. Color exists only when these elements align. Color does not enter the world as an extra ingredient, nor does it sit concealed inside objects. It arises through lawful interaction unfolding across scales. What seemed like a simple surface feature is instead the outcome of coordinated quantum events extended through space and biology. There is a quiet inversion at the center of this story. We often think of constraint as limitation, something that reduces possibility, something that narrows what can occur. But here, constraint is what makes color possible at all. If electrons inside atoms could absorb any amount of energy continuously, then incoming light would not be selectively filtered in precise bands. Absorption would blur smoothly across the spectrum. Surviving light would not carry distinctive imbalances. If photon energies were not tied to specific frequencies, light would not present structured options for interaction. There would be no discrete matching between incoming energy and electronic transitions. If your retina sampled the full spectrum with infinite resolution, metamers would not exist. Every distinct spectral distribution would appear distinct. The compression that makes color categories stable would dissolve. And if your brain did not adjust perception relative to environmental illumination, color would fluctuate chaotically with every change in lighting condition. At each stage, limitation produces order. Quantum rules restrict electrons to allowed states. Electromagnetic structure restricts photon energies. Biological design restricts sampling to 3 overlapping channels. Neural processing restricts interpretation through contextual stabilization. These constraints do not erase richness. They generate it. Because absorption is selective rather than continuous, materials differentiate themselves visually. Because perception compresses spectral complexity into relational ratios, stable color categories emerge. Because the brain compensates for illumination shifts, the world appears coherent rather than unstable. Color is not the absence of constraint. It is the expression of constraint layered across systems. What began as a failed intuition about stored redness has unfolded into a picture where limitation is productive. The visible world depends on exactness. Selective absorption depends on quantized energy gaps. The shaping of the spectrum depends on that selectivity, and the experience of color depends on that shaped light, meeting a biological system capable of sampling it. Constraint is not an obstacle here. It is the governing law shaping what can appear. We return to the apple, but the mental picture has shifted. At first, redness seemed like something the apple possessed in the same way it possesses mass or shape, a feature embedded in its surface, a quality waiting to be noticed. That idea felt stable because everyday experience rarely challenges it. But once the conditions were adjusted, stability began to dissolve. Remove light and the color disappears. Alter the illumination and the tone shifts. Analyze the light and it reveals internal variation. Examine matter closely and you find discrete energy thresholds rather than smooth receptivity. Examine perception and you find sampling and reconstruction rather than direct capture. What seemed solid turned out to depend on alignment. The apple's molecular structure determines which incoming photon energies are taken in and which continue outward. The outgoing distribution carries an imbalance shaped by that selection. Your retina does not decode that distribution in full detail. It reduces it to comparative activity across 3 receptor classes. Neural processing then stabilizes that activity relative to its surroundings. At no single point in that chain does redness sit as a contained substance. What exists physically are energy transfers, constraints, and patterned responses. The word red refers to the stable experiential outcome of that patterned interaction. It is not stored inside the apple. It is not traveling intact through space. It is not printed onto the retina. It is the perceptual expression of structured energy encountering structured matter within a structured biological system. The simplicity of the original belief has been replaced, not by confusion, but by layered coherence. Color is no longer something the apple has. It is something that happens. We began with an assumption that felt effortless. The apple appeared red because redness seemed to belong to it. The surface looked as though it carried color the way it carries texture. Careful examination changed that picture. Light arrives carrying discrete amounts of energy tied to frequency. The molecules in the apple contain electrons restricted to specific allowed states. When incoming photon energies match the gaps between those states, absorption occurs. When they do not, the photons continue outward. The light that leaves the apple is therefore not identical to the light that arrived. It has been selectively reduced according to quantum constraints inside matter. That modified distribution enters your eye. 3 classes of photoreceptors respond with different sensitivities across the spectrum. Their activity forms a ratio rather than a detailed map of the full spectrum. Neural processing evaluates that ratio within the broader visual scene and stabilizes it against changes in illumination. At no point in this sequence does color exist as a stored substance. What exists are energy transfers, permitted transitions, constrained sampling, and comparative interpretation. The stability of red depends on the alignment of all these conditions. Change the molecular structure and different photon energies survive. Change the receptor sensitivities and the same spectrum produces a different perceptual outcome. Remove light entirely and the experience does not arise at all. Color is therefore not a primitive ingredient of the universe. It is the experiential expression of quantized energy interacting with structured matter and structured biology under lawful constraint. When you look at the apple now, you are witnessing that alignment in action. The redness you see is the visible signature of quantum rules operating quietly beneath everyday perception. What once seemed like a simple surface quality resolves into coherence across scales, and that coherence is what makes the visible world possible.